information from your loading vectors. You can see there's a little bit of semi-annual built in. So that's a feature of these CSEOFs, that any signal that's a integer multiple of the nested period, or a factor of the nested period, will also be built into that same loading vector. All right, so your second mode from the CSEOF analysis of the satellite altimetry data will be related to ENSO. So you can see this high spot in the Eastern Pacific weakens during the summer before strengthening in the winter again. And a 2-year nested period is actually a little bit better for this, but just for ease of showing the CSEOF analysis, I'm just using the same 1-year analysis. With the 2-year analysis, you could get the you could show shifting from an El Nino to a La Nina and then back to an El Nino within that 2-year period. And again, if we combine this information, so here's a PC time series. You have your strong ENSO event in 1998. This is the contribution of ENSO of El Nino to global mean sea level. And this figure didn't show up that well, but this is just a similar analysis done just around the United States. You can see fairly large scale coastal, or fairly large magnitude coastal signals associated with ENSO, less so on the East Coast, which is makes sense since it's a Pacific feature. And we have this representation. So this is computed from the reconstruction itself. So again, we can pull out the ENSO signal with the CSEOF analysis when focused on a specific location.
Sorry, Ben, can you go back to that last slide? So
Yep.
the blue and the red in the bottom graph, which is ENSO, which is the...
Yeah, so the red is the CSEOF PC time series. The blue is the MEI, the multivariate ENSO index, which tracks. It's a commonly used index for tracking ENSO. So you can see the two agree very well, which, I mean, this is giving us confidence we're capturing ENSO within our reconstruction, which I'll talk about a little bit more in just a second. All right, so we created the CSEOF reconstruction, and this is just some details. I won't get into them in depth. But we created a CSEOF reconstruction from 1950 to present. We only had to use 11 CSEOFs, so this is a nice feature of CSEOFs versus EOFs. 11 CSEOFs give you 80% of the variance in the satellite altimetry. You need hundreds of EOFs to do the same thing. And we're selecting 412 tide gauges from 1950 to present that we're fitting to. And in a recent study, a graduate student at the University of Colorado found the CSEOF reconstruction outperformed the EOF reconstruction based on a number of tests that he did. So in an idealized setting, he used the satellite altimetry data, subsampled it to create synthetic tide gauges. So using the historical distribution of tide gauges, subsampled the altimetry data to create synthetic tide gauges, and then fit basis functions, created a reconstruction that he can then compare to the truth of the altimetry. So here's some of those results. So this is truth. This is your 20-year trends from Aviso, from the satellite altimetry. Based on the 1930 tide gauge distribution, this is what you get from EOF analysis. He probably didn't reduce the variance the way you should have, so you end up getting a lot of overfitting in the EOFs. But with CSEOFs, you don't get the trend pattern. You get a fairly good representation of the trend pattern, but not necessarily the magnitude. But you can see as you get into the 1970s and using all the gauges, you start to get a pretty good representation of the actual trend in altimetry, whereas you get much more noise with the EOF reconstruction. And again, this is just showing that the CSEOF reconstruction gives you a good representation of global mean sea level. So this is detrended global mean sea level. The blue is the Aviso, that's truth. And this is for a CSEOF here. So the dotted is with the 1930 tide gauge distribution. Green is with all the tide gauges. So you can see you're reproducing that very nicely. With the EOF, you can see at the 1930s distribution, again, you're getting the overfitting associated with that. A fair test would probably be to reduce the variance you're fitting with the EOFs, but again, it's the idea that you have to make adjustments when doing an EOF reconstruction based on the...
You just mentioned the magnitude.
Yeah.
When we're looking at the maps, are those in the same units as the graphs you just saw, centimeters, or are
These are in centimeters per year, yeah. Yeah, sorry. Yeah, I'm just referring to, if you look at this feature here, you obviously have a weaker trend than you do in this one. So, but yeah, these are the same units. And so he performed, I don't expect you to read all of these, but he performed 17 different tests in all, adding noise to the synthetic gauges, using different, the distributions from different decades, and comparing to some kind of basic metrics for evaluating the reconstruction. So he correlated what you get from the reconstruction with truth for global mean sea level, the Pacific Decadal Oscillation, the Atlantic multi-decadal oscillation, and a couple of different ENSO metrics. And in every one of these cases, the CSEOF analysis outperformed the EOF analysis. So long story short, we have pretty good confidence that the CSEOF reconstruction is performs better in terms of the representation of climate variability than an EOF reconstruction. And just as a little side note in these next 4 slides, I'm not actually going to talk about this beyond just these few slides, but we've also done work reconstructing sea level before 1950. So usually when we talk about sea level before 1950, we're just talking about global mean sea level. You don't have enough tide gauges back through time. So here's your distribution of tide gauges. This goes back to 1800, but even in 1900, you can see we have about 100 tide gauges available to us. And that number increases fairly rapidly, and particularly after 1950, that number goes up. So before 1950, the idea is you really don't have enough tide gauges to reconstruct regional variability. So what we can do is with the CSEOF analysis and building in a simple regression technique, we can use measurements of other climate variables to reconstruct sea level before 1950. So here we're using historical sea surface temperature, SST measurements, to improve sea level reconstruction from 1900 to present. And the motivation for this is simply that you have many more SST measurements back to 1900, and these are taken in the interior of the ocean basins. So they're much more useful than the respective tide gauge measurements that we have. So to do this, just a very simple regression technique. The goal of the reconstruction is just to reproduce your PC time series back through time, right? Your spatial patterns are the same. You're just trying to reconstruct the temporal variability back through time. If we can create spatial patterns in SST and sea surface temperature that have the same temporal evolution, the same PC time series as what we have in sea level, then we can use those loading vectors, those spatial patterns simultaneously to reproduce the variability and sea level back through time. So that's all this regression is doing. So you're taking CSEOFs from SST, regressing onto each individual PC time series from sea level, getting this set of regression coefficients. You then apply these regression coefficients to the loading vectors, and you come up with regressed loading vectors. So these loading vectors here have the same, or at least within the regression constraints, the same PC time series as the sea level, as a corresponding sea level CSEOF. All right, so just as an example of this, so we did a sea level reconstruction. So this is the truth. This is a VSO. And this is with actual tide gauges and actual SST. We're just looking at the time period from 1993 to 2011. So this is with tide gauges only. So we're only using sea level measurements here. Here we're only using SST measurements. And here we're using tide gauges and SST. So we're using as many observations as we can. And you can see that with sea surface temperature alone doing this regression, you can actually get a pretty good reconstruction, at least in the last 20 years of sea level. So you don't even really need any sea level measurements directly to get a good representation of the trend pattern in the past 20 years. And you see we're doing even better when we combine all of them together. And again, similar to one of the previous slides, I'm looking at a number of metrics. So the multivariate ENSO index tracks ENSO variability. So this is with tide gauges only, this is SST only, and this is the two of them combined. And you can see over the full record, the two combined outperform tide gauges on their own. So if we're trying to reconstruct variability back to 1900, we can play little games like this where we can incorporate other climate variables to improve our reconstruction. All right, so all that being said, let's get to how we can actually use these sea level reconstructions. What can we do with them, and how can we pull out the sea level signal associated with climate variability? So why do we care about variability on interannual to decadal timescales when studying sea level? One of the big reasons is we only have a 20-year record from satellite altimetry. So we know this trend pattern is going to have the impact of climate variability on it, right? So this hotspot here, the question can easily be asked, is that related to anthropogenic warming? Is that a long-term trend that's going to continue? Or is this just simply a climate signal that we've managed to sample 20 years in a single phase of that climate signal, and it's contributing this trend? And as I showed earlier, some of the tide gauges have very short records that are heavily impacted by short-term signals. So if we use those gauges in our reconstruction, or if we're using them to global mean sea level, are they really giving us a good representation of the long-term trend, or are they just showing us a trend related to climate variability? So using the sea level reconstruction, we asked three specific questions. So how have regional sea level trend patterns changed during the past few decades? What are the characteristic timescales of changes in the sea level pattern? And what are the factors driving the changes to the trend pattern? So we have this trend pattern, and we want to know if this is really unique. Is this something that we've only seen, that's only been observed in the ocean in the past 20 years, or has a similar pattern of this popped up over the last century? So using the sea level reconstruction, we can start to answer that. So we're using two different sea level reconstructions, the CSEOF reconstruction, which I've already talked about, and probably the most widely used, the Church and White EOF reconstruction. And as a first step, we computed 20-year trend maps from the two reconstructed data sets. So we averaged down to annual data, computed 20-year trend map, then stepped a year in advance, and set up a number of 20-year trend maps from 1950 to present. That gave us 41 trend maps in total. Obviously, these aren't independent since they overlap, but it gives us a time series of trend maps, 20-year trend maps that we can then analyze. So as a first check, this is just from 1993 to 2011. This is of ENSO, what's actually measured by the satellite altimetry. This is our reconstruction over the same time period, and this is the EOF reconstruction. So you see the three are agreeing pretty well over this time period. It's just a first initial check to make sure that our reconstruction is doing fairly well. Yep.
They agree pretty well in the tropical Pacific.
Yeah.
Look at the Kuroshio area.
Right.
There'd be good agreement at all there in the northern part.
Yeah, these, there's some questions. I mean, you really can't use these reconstructions to look at such high-frequency variability like in these areas. You get another area that is probably of greater concern is the Indian Ocean. So you see our reconstruction here has this negative trend, whereas in the Indian Ocean you don't see that in the EOF. And you get something similar in the EOF reconstruction. So
Tropics are good looking mid-last.
yeah, I mean, that remains to be seen. So one idea that's thrown around is that you reconstruct specific ocean basins. You don't do a whole global reconstruction. So if I'm interested in the Indian Ocean, I'll focus on the Indo-Pacific, for instance, or just the Indian Ocean. But yeah, I mean, the Kuroshio doesn't necessarily concern me as much as something that we're seeing there in the Indian Ocean. I wouldn't expect to do that well on the higher frequency variability. But there are some areas of concern. But most of what we're doing that I'll be talking about is actually focusing on the tropical Pacific. So I think for the purposes of today, we're okay. All right, so we took the EOF trend map, we took this, and we correlated it with each of the 41 20-year trend patterns that we have from the reconstructions. And this is what you end up with. So blue is the CSEOF reconstruction, green is the EOF reconstruction. You can see this last point is basically the correlation between these. So it's fairly high here. But you can see back in the 20-year trend map centered around 1965, we have a similar peak. And if we look down at the actual trend map from 1957, 1976, we see a very similar trend pattern to what we've seen in the last 20 years. So that suggests that this trend pattern we've seen from EOF is not unique. It's shown up in the past and even flip signs. So the trend pattern from 1968 to 1987, we basically have the reverse of this pattern with much lower sea level in the western tropical Pacific and higher sea level in the eastern tropical Pacific. So we know that this trend pattern has basically come in and out of in terms of dominance. But what is the dominant 20-year spatial trend, pattern of trends? So to do that, we did created the same 41 trend patterns from 1950 to present, and then we performed an EOF decomposition. So we wanted to see what the pattern that captures most of the variance in these 20-year trend patterns actually looks like. And this is what you end up with. So here's your mode 1. So this is your dominant mode. Mode 2, Mode 3. So these are your three dominant modes. And you can see in Mode 1, this looks a lot like our EOF, what we've seen over the past 20 years. So this suggests this is our dominant, what we've seen in the last 20 years is the dominant trend pattern that we've seen over the past 60 years. These are the PC time series associated with these. I'm not going to talk about those specifically right now, but we can then ask the question, can we attribute any of these modes to natural climate variability? So we know what these look like spatially. We have some temporal representation of them. Can we relate these to any kind of climate signal? So if we look at that first mode, so taking the first mode, the PC time series is here in blue, and we look at the PDO. So we're taking 20-year trends in the PDO, plotting those against this mode 1, our first dominant trend pattern mode, and you see the correlation is very high. We only have about one cycle of this, obviously, but they're very nicely in phase. Show very good agreement, a correlation of 0.96, which you could easily eyeball. We also get the kind of horseshoe pattern that you'd expect from the PDO in the North Pacific. So based on this simple test, based on the information we have from the spatial pattern, what we have from the associated PC time series, we see that this mode agrees very well to the PDO and is related to some kind of low frequency variability in the Pacific Ocean. So we can take this a step further. So knowing that this mode is related in some way to the PDO, and taking the global mean of this loading vector, we can evaluate the contribution of the PDO, by extension, to global mean sea level. So taking the spatial average here, multiplying by this last point, we can get an idea of how much the PDO has contributed to our 20-year satellite altimetry record. And this is what you end up with. So mode 1 is this solid line. So you can see that in the past 20 years, the PDO has contributed about 0.5 millimeter of the 3.2 millimeters per year, or has contributed 0.5 millimeter per year to the 3.2 millimeters per year we've observed from the satellite altimetry. And based on the reconstruction, this red is the full reconstruction. So that's the 20-year trends in our global mean sea level from the reconstruction. Blue is the sum of the first 3 modes. So you can see very clearly the first 3 modes are capturing most of the trend variability in global mean sea level. So just to put this into words, a little bit clearer, in the past 20 years, the PDO has started to shift from a positive to a negative phase and has contributed about 0.5 millimeter per year to global mean sea level. So what this means is that the long-term trend in global mean sea level, the one that might be expected to continue in the future, is going to be closer to 2.7 millimeters per year as opposed to the 3.2 millimeters per year once you've removed the contribution of the PDO. And similarly, if we look at a time period, so if we look at this time period, from 1968 to 1987, when the PDO went from negative to positive, the PDO lowered the trend in global mean sea level by 0.7 millimeters per year. So you can go back and look at this, pick out different times where the PDO has contributed significantly, and it gives you a slightly different interpretation of what we've measured, what we've reconstructed in terms of global mean sea level in the past 60 years. And also, if we extend this to the acceleration, if we remove the PDO, the acceleration, just based on a very naive, simple quadratic fit, goes from 0.04 millimeters per year squared to 0.02 millimeters per year squared. So once you remove contribution of PDO, you basically cut your acceleration in half. All right, so as an additional step, we can try to assess what does the PDO contributed to regional sea level trends. So we've estimated what it contributes to global sea level trends here, but what about to regional sea level trends? So what we can do, we take this loading vector, this spatial pattern, and we can project it back on to the satellite altimetry data. So it's computed in trend space, but there's no actual units on this. So we can just take this and directly project it onto sea level. And this is what you get back. So blue is what we get from our projection. So we've taken that spatial pattern, fit it to the altimetry data. You end up with this blue time series. You can see it matches the PDO fairly well. Because we've arrived at that spatial pattern because of that 20-year trend. From the 20-year trend, you have some smoothing associated with it. So we do miss some of these large events in the PDO. So we mainly have the low frequency portion of the PDO. And you see there's very clearly a trend associated with this over the satellite altimeter record. We take that trend and we combine it with our EOF loading vector, and this is what you end up with. So this is the PDO contribution to regional sea level trends from 1993 to 2013. And this is the ENSO. So you can see in the Western Tropical Pacific you have some very similar patterns, but it doesn't appear to explain all of this pattern in the Western Tropical Pacific. So the conventional wisdom was that when the PDO shifts phase, this whole hotspot in the Western Tropical Pacific is going to flip signs. You're going to have decreasing sea level. So say the people in Indonesia, the Philippines wouldn't be as concerned about sea level in the next 20 years as soon as the PDO shifts phase. So we've actually estimated the contribution of that based on our analysis of the PDO to sea level trends. And if we then difference the two, what you end up with. So we've removed the contribution of the PDO to regional sea level trends from the ENSO. And you can see that in Indonesia, you've lowered sea level significantly. So if you remove the PDO influence, sea level becomes much lower. You get rid of the hotspot. But off the Philippines, you have this much larger, or you still have a persistent large feature that, unless it's explainable by some other type of climate variability, you could expect to continue at least into the near, more immediate future. So removing the contribution of this natural variability allows us to isolate the secular or non-periodic trends in sea level. So I'm not saying all of this is non-periodic, but at least we have a better idea of what that non-periodic, that pattern that will continue in the future actually is. And we did one final test. So to try to understand this pattern and try to attribute it to anthropogenic forcing. Sorry, I didn't remove that one. I probably should have. But we did a very simple model experiment. So there's been a number of studies that have looked at the Indian Ocean and related a half degree of extra warming in the Indian Ocean to anthropogenic forcing when compared to the Pacific Ocean. So if we do a very simple model and use that half degree of warming to drive the winds and do a control run where we don't have that half degree of warming, difference the two, and compute the sea level trends resulting from that, this is the pattern you end up with. So you can see you have this hot spot off the coast of the Philippines. You have a hot spot off northeast Australia. There's some pretty good qualitative agreement between the two patterns. So in this sense, as much as you believe this agreement, we can begin to attribute this pattern to the warming in the Indian Ocean and thus to anthropogenic forcing in the Indian Ocean that's driving these wind patterns. So this is one of the first attempts, at least that I'm aware of, in looking at mainly an observation-driven approach to actually try to explain some portion of the solid altimetry trends, the regional variability, that's related to anthropogenic forcing. So we've tried to isolate that by removing natural climate variability and doing the simple model experiment. It provides us some confidence that we're actually uncovering what could be expected to continue into the future and not simply going to flip sign or decrease related to natural variability. So just to give a quick summary, so sea level reconstructions provide the opportunity to extend the sea level record, and that gives us the opportunity to extract lower frequency, long period climate variability from the long records. We can then remove this variability and get a better idea of the underlying climate change signal, so what would be expected to continue as a result of anthropogenic forcing into the future. And this could also improve the ability to do regional sea level projections. So these are just fingerprints for the ice sheets, the glaciers, and ocean dynamics. And by removing the impact of climate variability, you simplified this problem. So now you only have to really, not that I've explained all of the climate variability, but if you could, you then have to worry about fewer components contributing to regional relative sea level rise, and the projection problem becomes a little bit easier. And relying on these reconstructions to extract low frequency variability also gives us a better interpretation of the shorter solid altimeter records. We're limited by the 20-year record. It's going to keep growing, hopefully, I guess, pending the funding of more satellites, but it'll continue on into the future, and we'll be able to do these studies more directly on the altimeter data. But until that point, we need to rely on things like sea level reconstructions to create a longer record that we can go in and analyze. And as a final note, these sea level reconstructions also give you a chance to validate and evaluate the quality of climate models. So these efforts, while I only talk for the most part about observations and a real observation-driven approach, it does go hand in hand with the work that climate modelers are doing. These provide a good verification for the work that they're doing and the sea level estimates that they're producing. And that's all I want to cover for today. Thanks.
All right, we have plenty of time for questions, so I'm going to have Gene go first, and then Gary.